Okay, well, I'm really pleased to virtually welcome Grant Allen to SoMAS to give today's seminar. Grant is Professor of Atmospheric Physics at the University of Manchester. He started with a PhD at Leicester, developing satellite retrievals for PAN, and it seems like he's gradually been working his way down towards the Earth's surface, because he then went on to study polar stratospheric clouds before moving to Manchester to investigate pollution transport in tropical convection. He then went on to develop trace gas retrievals for remote sensing instruments on aircraft, but more recently his research is focused on more on in situ measurements of greenhouse gases and on the quantification of greenhouse gas emissions. Grant's been PIing and co-I of over 10 projects recently to study greenhouse gas emissions at local, regional and global scales. And he's going to talk today about the ongoing MOYA project, which aims to improve our understanding of the global methane budget. Grant was also my PhD supervisor, and he gave me my first job. We've kept in touch, but I'm interested to hear about all the things that have been going on since I left the group. So yeah, take it away, Grant.
Thanks, Joe. Thank you for inviting me to come and talk to you today. So the first half of the talk I'm going to give will be a story of the state of what we know about the global methane budget. And then I'm going to tell you a story about what we've been doing in Africa to try and improve that picture. So the photograph in the background that you can see here is a photograph taken from 1,000 feet over Lake Bangweulu, which is in Zambia, which we've measured, hosing out methane into the atmosphere. But as you'll see later on in the talk, we really need to understand just how much this could be contributing to the global budget and what it means. So I'm not going to talk about who's contributed to this at the end, because there's about 50 odd people. So there's a slide at the end telling you who's involved. But there's a very big team behind us here who operate the aircraft, who run the models, who do the measurements and do the analysis, not least of which is your very own Joe, who was here in Africa with us in 2017 to 2019. Right, so the scope of the talk is really about, well, why do we care about methane? I'm sure most of you know about that, so we'll cover that very quickly. What we know and don't know about the current global budget. I'll then show you these aircraft surveys of fire and wetland emissions in Africa and the tropics that we've been doing, and talk about what I think we still need to do, and what the unanswered questions are, and what direction we're going in. Right, so methane, we call it a natural gas. I'm not entirely sure why we call it a natural gas and why other gases aren't natural, but there we go. It has many sources, and these pictures really sum up all of those sources. So going from the top left, we have emissions from the seabed geological seeps, rice paddy fields, oil and gas facilities. I know a lot of you guys there at Stony Brook are involved in the fossil fuel industry emissions or urban emissions. We've done a lot of work looking at that as well, but I'm just going to talk about natural sources of methane today. Domestic use of gas, cattle, agriculture. The picture in the bottom left is one that Joe I know will hate. That's a picture from a landfill site where I dragged everybody to a very smelly landfill site in southern England in 2014, trying to work out how we use flux approaches at the scale of a landfill site, an extremely hard challenge actually. Biomass burning and methane hydrates, one of the big threats to us perhaps in probably the relatively long-term future. So why do we care about methane? So it's second most important greenhouse gas after CO2. It has potential feedbacks, which is really the theme of what we'll get onto in the second half of the talk. There's perhaps some evidence that some of these feedbacks on natural methane sources have already been triggered, I would say. So positive temperature and meteorology feedbacks, rainfall and temperature. And it also has an impact on air quality because it consumes OH. So it affects the global hydroxyl budget, which can result in changed concentrations of other pollutants. And typically methane is co-emitted with other nasties that we don't like, volatile organic compounds, higher order alkanes, alkenes, etc. So what do we think we know? Well, we know very well what's in the atmosphere right now. We can measure that, and we've got a fairly good handle on where it comes from, but but only partly, and we'll look into that in a moment. So how do we know this? We know it through process studies and case studies, the long-term data sets and networks that we've got that we're adding to all the time, and through budgeting models and climate models and reconstructions and predictions. And I should point out that for those of you that do know Joe in the Stony Brook group, I guess he's been in lockdown most of the time he's been working over there with you. But if anybody gets bored with the presentation, you can play a sort of Where's Wally competition with these photographs. So there's your first one. That's a gift in the bottom right. That's a field site that we set up in Blackpool in Lancashire in the UK. So this is a fence line monitoring site of the UK's first fracking site that was taking part just in the field to the right of that photograph. And what we know we don't know. So I'm using the, for those of you who can remember Donald Rumsfeld, the Donald Rumsfeld taxonomy here. So what we know we don't know. We know that we don't know the relative proportions of the sources and sinks. And that applies now and in the recent past. And we even less well know how those sources and sinks may change in the future. So again, why should we care? Second largest contributor to warming in terms of radiative forcing. So there's a plot from the IPCC Assessment Report 5. It's 21 times more effective than CO2 at trapping infrared radiation, molecule for molecule, with a global warming potential over 100 years of between 28 and 36 times that of CO2. And it's accumulating faster, relatively, and I'll come back to what relatively means, than any other greenhouse gas. But it has a smaller lifetime of 12 years. So CO2, 100 years, nitrous oxide, 1,000 years. Methane has the lowest lifetime of the major greenhouse gases, which makes it the perfect target for getting us some quick wins on climate. If we can reduce emissions of methane now, that will disappear from the atmosphere very quickly compared to CO2 and nitrous oxide. And I said relatively there, I just want to qualify what that means. That doesn't mean in mass terms, that means in percentage change in concentration year on year. Methane is the gas that's changing fastest in terms of its percentage change in concentration year on year. So it's a gas that we need to be concerned about. And this plot, which is a very recent plot from the NOAA team, shows the recent methane trend globally. So this is a global average of all of the measurements at global atmospheric watch stations. And you can see there a few interesting features which we're going to look at. Growth between 1984 and about 2000, some sort of plateau between 2000 and 2007, and then a rise which has recently started to accelerate. And 2020 has seen the largest growth in global methane, 15 parts per billion in 2020 alone, the largest growth that's been seen in the modern record. So that's what we know. We can measure that. But what about it don't we understand? We know what's there, but we don't know what's causing these changes. So this plateau between 2000 and 2007, which actually saw 3 years of declining global methane, is still a mystery to us. There's plenty of theories on exactly what caused that, the decline of Russian gas and coal in developed nations. And then the rise since 2007 is what sparked a lot of recent interest. So science lost a bit of interest really during this plateau. We thought that somehow the natural environment had found a new equilibrium with methane, and it kind of went off the radar a little bit. But then it started rising in 2007 and attracted a lot of interest. And there's a lot of interesting features about that trend since 2007 that tell us about how the sources in particular are changing. And we're going to look at those. So what we don't know is what methane will mean for climate change going forward. So we can predict human trends in emissions through IPCC scenarios and storylines. But it's very hard to predict what the trends in the natural emissions of methane might be going forwards, and we'll see why in the second half of the presentation. And what climate change means for methane. So positive and negative feedbacks, regionally and biomically. So some places, some soils can be a sink for methane. Some very interesting thoughts on what might happen in the Arctic in the medium term in terms of negative feedbacks actually. We can talk a little about those at the end if somebody wants to ask a question. And in the tropics, there may be positive feedbacks with increased rainfall and temperature. More long term, there's huge stores of methane in permafrosts and clathrates. And of course, there's the changes in wetland extent, natural, and our changes in human use of agriculture and what that means. And methanogenic and methanotrophic activity, the microbes that control the methane that's emitted from the soils to the atmosphere. There's a lot of debate over what will happen in the balance of methanogenesis and methanotrophy in particular. So if we look at the global methane budget then, so this is a schematic of the sources and sinks. So the sinks are stratospheric and tropospheric OH, mostly tropospheric OH, which by far dominates the sinks of methane in the atmosphere, and tropospheric chlorine as well to a lesser extent, and some oxidation in soils. And the sources are all these ones in the middle. Don't worry about the numbers. We'll have a little look on the next slide at some of those numbers there. But all of those ones we've mentioned already: geological sources, fossil fuels, wetlands, landfill and waste, fresh waters, rice, livestock, and hydrates. But the thing to draw attention to here is the stores. So in the Earth's surface, in the form of permafrost hydrates, gas reserves, and ocean hydrates, there are thousands of years of equivalent global methane budget stored in the terrestrial environment. And it's these ones that we should be worried about with perhaps more medium and long-term climate change and liberating those. And of course, gas reserves account for 1.5 million teragrams is something that we want to keep in the ground if we're going to limit climate change in the near future. So if we look at these with some photographs, this helps us look at what the big sources really are. So we've seen these photos before already. And the ones to draw attention to are the wetlands. So of a budget of around 550-ish teragrams of methane to the atmosphere per year, wetlands account for quite a large fraction on that. But you can see the big range there of uncertainty we have on wetlands, by far the largest range of uncertainty. And the two other big ones are agriculture and fossil fuels, of course. So we're going to talk just in this talk just about the wetland sources. But those other sources we absolutely do need to worry about. So where is this methane coming from? So this is quite an old plot now. This only goes up to 2008. So the x-axis here runs from 98 to 2008. The y-axis is latitude, and the z-axis is the methane concentration, which is also color-coded for you. So really, the thing to take away from this is that the sources are predominantly in the northern hemisphere. And there's a seasonal cycle on there that you can see. Methane accumulates in the winter months and declines in the summer months. And that's because of the nature of the sources, but also the OH sink. So the more sunlight, the higher the sink rate. So we can see from this alone that the sources are most predominantly in the northern hemisphere and terrestrial. And then this, if I can get it to work, let's see. This is always the issue, isn't it? There we go. Right, so this is a model simulation by Matt Rigby from the University of Bristol using the Mozart model, just using emissions inventories to look at how methane mixes in the atmosphere with time. So you can see there labeled some of those key sources: fossil fuels, clathrates, minimal wetlands, fossil fuels. And you can see the big emitters in China and India associated with rice and fossil fuel burning. And you can see the southern hemisphere boundary. So the equator acts as a really nice barrier to mixing between the hemispheres. And because methane's lifetime is only 10 years, and the timescale of mixing between the hemispheres is similar, we maintain that concentration gradient between the hemispheres quite nicely. And that's why you see what you saw in Ed's plot of the hemispheric concentrations. So why don't we know everything? Why isn't this already a done deal? So you do not need to analyze the plot on the left. This is it's a contour plot of methane change per year with time and latitude. And it basically just telling us there's an enormous amount of detail buried in this, and we can't unpick it. It's very difficult to reconcile every contour in that plot. But that's the holy grail of global methane budgeting, is to be able to reconcile every contour that we see in a plot like this. And that's what we're working towards. So how do we get better at doing this? So recently, so really only since the start of this century, we've had good measurements of carbon isotopes in methane. And the isotopes offer us a gift because different sources of methane have different isotopic weight. So biogenic sources are typically more depleted in carbon-13 relative to the thermogenic sources, so the fossil fuels that are roughly 30 to 45% of the global methane budget. So the range is on the top of that plot there, which is a figure from a Nature paper in 2016, which captures the range of uncertainty that we have in the current budget. 55 to 70% of the global methane budget is biogenic methane, and 30 to 45% of it is thermogenic methane. And that's a result that has been produced by using carbon isotopes to co-constrain the methane budget. So if you look at trends of methane concentration, and you also look at the changes in isotopic composition of the methane in the atmosphere, you can get some really powerful clues on what the sources are. So big thing to hold in mind for later in the talk is that biogenic sources are depleted in carbon-13 relative to thermogenic sources of methane. And this is the seesaw, if you like, that a lot of us are working on trying to improve, is to build up a clear picture of what the ranges or the PDFs of the different isotopic compositions of the different sources is. Because if we do this, we can balance the global methane budget using isotopes and knowledge of the sources alone. So the bulk atmospheric composition at the moment is around minus 47.3 per mil. There's the effect of OH, the reaction with OH means that there's fractionation from what it would be, which would be 53.6. It makes it slightly heavier at 47.3 because of the nature of that reaction. But if you look at this seesaw, what you can see on the left-hand side is that all of those microbial biogenic emissions, ones associated with methanogens in soils and wetlands, are lighter than the current observed bulk methane source. And fossil fuels are on the right-hand side. They're heavier than the global bulk source. So if we can see which way that trend is going, if the methane in the atmosphere is getting lighter or heavier, it tells us about how the relative abundance of those sources is changing with time. And the other thing to draw your attention to is the biomass burning. So when the vegetation burns, that's extremely heavy, even relative to fossil fuels. So there is a lot of debate at the moment about whether biomass burning changes might be driving some of the trends that we're going to have a look at. But as scientists, what we're trying to do is improve this picture, get some better distributions of what the carbon isotopic compositions are for the different sources contributing to the atmosphere. And this is why. So if we look at this, we can see the methane trend on the left, and we see that plateau between 2000, 2007. And on the right-hand side is the carbon isotopic composition of the atmosphere over the same time frame. And you can see that from 1980 to around 2007, it was gradually getting heavier. Okay, which would be consistent with an idea that fossil fuels, for example, or fossil fuels plus some combination of biomass burning would be dominating to cause that change to get heavier with time. But something strange happened in 2007, and that's really what we're working on now. And that is that methane in the atmosphere suddenly started getting lighter. It started getting depleted in carbon-13. So because we know that biogenic sources are depleted in carbon-13 relative to the bulk molecular mass, that suggests that in 2007, the seesaw tipped and that there was faster relative growth in biogenic emissions compared to thermogenic emissions. And there's a message I want to get through a few times in this talk, really, and we need to be careful on when we say that biogenic emissions now dominate. It doesn't mean that thermogenic emissions and fossil fuels don't matter. All sources are rising, just some sources are rising faster than others. Okay, so what this picture tells us with the isotopes is that the biogenic sources are probably growing faster than thermogenic sources are since 2007. But there's still debate around that. So there's debate around the role of the hydroxyl sink and if that's been changing, whether biomass burning might have decreased in that period, which would drive the bulk molecular mass lighter as well. So there is debate, but I think there's a growing consensus around this idea that it's a relative growth in biogenic emissions since 2007. So let's look a bit more recently again. So this is on the top, you can see a more recent plot of the methane trend and the isotope measurements that we have since 2000, showing that consistent monotonic decrease in carbon-13. And then on the bottom right, this screen-like plot that, you know, now we need to have a little look at in a bit more detail. So much of the recent growth in global methane has been driven by the southern subtropics and tropics. And you can see here that there's blobs here where we see growth in the northern tropics and even in the Arctic in 2014. That got a lot of people very worried. But since 2017, there's evidence of growing emissions in the southern hemisphere now, and especially in the southern tropics and subtropics. So the summary to take from this is that current methane budgets are not co-constrained by isotopic balance, and the source isotopic signatures are poorly known, especially in sub-Saharan Africa and South America. So a lot of the work we've been doing is trying to get a better handle on what's going on in the southern tropics, so in Africa and South America, and those are the results we're going to have a look at very shortly. But just before we conclude the story on global methane, there's another clue. So as well as the isotopes of carbon that are becoming lighter, there is also this picture. And we see here that ethane is very well correlated with methane up until 2007 as well. And then for 2007, we see the increases in methane, but they're not correlated with increases in ethane. And ethane is co-emitted with fossil fuel methane, roughly about 10% of global gas reserves are ethane. So we also see some disconnect between the fossil fuel story here as well in ethane, not just in isotopes. And because we've been doing some work on fracking, I thought I'd show this. And I know there's lots of people in the US still working on fracking emissions. So I just wanted to show this very old plot now from 2014 from a talk I gave to the NSF, which at the time was quite provocative. So it shows methane trends up until 2013. So we're looking just over a few years, 2000 to 2013 here. And on the bottom right is the same time period, but the growth, the ballooning of US shale gas. And that looks nicely correlated, but we all know that correlation doesn't mean cause. And I think the isotope story since then has told us that trend, which at the time was very closely aligned to fracking, and people really thought it might be US fracking, it probably is not the case. So should we worry about fracking? I'm sure a lot of you have seen this quite famous plot from Eric Kort's paper in 2014 showing detectable methane emissions from space in the four corners. So should we worry about methane? Well, yeah, from fracking? Yes, of course we should. All sources matter. And some sources matter more than others. So natural emissions are higher than fossil fuels. But the natural sources aren't really under our control, whereas emissions from thermogenic sources, fossil fuels, they are under our control. So the answer to that question, should we still be worrying about fracking? Yes, of course we should. Right, so moving on to a bit to the second half of the talk. Quantifying emissions, a scale problem. This is quite an old slide, but it's still fit for purpose today. I wrote this slide 10 years ago. But the problem in how we characterize emissions and close global budgets really comes to what we can measure and how we can model it. So we can measure in situ very well. We can put instruments around fracking sites and landfill sites and measure fluxes with sometimes quite complex methods at the scale of, you know, a meter to a few hundred meters. And we can use satellites and global models to tell us about the picture from a few kilometers up to continental scales or global scales. But there's this missing link in the middle, really, of our knowledge of processes and measurements and models. So we still have this missing link in the middle where it's very difficult to extrapolate things that we might measure at the process level, even down to the level of what's going on with specific plants in a quadrat, you know, up to the scale of a few kilometers, and fill in this gap in the middle between what we can tell globally and what we can do in the middle. So the tools at our disposal to fill that missing link are using aircraft, remote sensing, which is getting better all the time. I think GHG, methane, SATCH, and the Sentinels are going to really help us. Sensor networks and drones, and the models. So there's lots of different models you can apply here. Coupled surface atmosphere models, process models, which try to parameterize what's going on with plants and wetland systems. We'll come back to those. Transport inversion models, which I know some of you guys at Stony Brook use. Co-constrained global budgeting, so these ones where you use isotopes, ethane and methane simultaneously, and then the climate scales. So how do we learn more about all of this? So moving on to what we did in the MOYA project. So the MOYA project, the acronym there means methane observations and yearly assessments. So I'm just going to present one part of it here. So the MOYA project consisted of over 12 UK universities and partnerships in Africa, e.g. with the Ministry of Mines in Zambia. And it was funded by the Natural Environment Research Council and took place between 2015 and 20. And it was really tasked with trying to get a better handle on the global methane budget. The PI of it was Ewan Nisbet at Royal Holloway. So I was the work package lead for the aircraft component of the project, which worked in Africa with the FAAM Aircraft. And we were using aircraft, satellite and ground networks and global and regional modeling studies to try and close the global methane budget. But the big focus of it was on tropical biogenic sources. So unlike previous projects that have looked at anthropogenic sources, here we really focus on biogenic sources in Africa and South America. Right, so now I want to show you a few photographs of our aircraft. I think you guys have your own aircraft that you fly around New York, the New York area. This is the UK's craft. It's a commercial, it still flies commercially. It's a British Aerospace 146 aircraft. You can see a photograph of it there on the top right. And it's been kitted out to take a remote sensing, trace gas and aerosol suite of instruments. So you can see the picture on the bottom right shows the cabin that's had the passenger seats ripped out and filled with racks and screens. And we fly with the cockpit door open. And we usually have somebody that sits behind the pilots that helps to direct the sampling that we do. And the photograph on the bottom left shows, you know, some of the things that we're able to do with this aircraft. It's flown by Royal Air Force test pilots mainly. And we can fly down to very low altitudes over the ground. So I think that photograph is with the aircraft just 500 feet off the ground. We can go down to 50 feet over the sea surface, which, as Joe will tell you, is extremely scary when you look out of the window. And if you can spot the obvious health and safety issue here, we also get served coffee on this flight. It's great. It has its own cabin crew member that will serve you sandwiches as well. So it's a great luxury to have. The photo on the top right is some of the cloud probes that hang down from the wings. So we do a lot of flying around the UK here, looking at cloud physics and meteorology. Unfortunately, because you're flying at low altitude, quite often around near to the coast, we often get phone calls to the police or the Coast Guard saying that there's an aircraft on a bombing run in southern England and worried about this. So our flight plans have to be very carefully coordinated with emergency services so that they know that those are not missiles on the side of our plane. The sorts of things we can measure are, I've underlined the ones that are relevant here. So methane, CO2, nitrous oxide. We have an Aerodyne QCL and ICL rack that can measure ethane, methane, isotopes of methane. But the in situ methane and CO2 concentrations are measured by a Los Gatos Research fast greenhouse gas analyzer. And we also measure trace gases relative to air quality, so CO, ozone, NOx. We can drop sons out of the aircraft to measure vertical profiles of thermodynamics. We can take whole air samples for offline analysis in the lab using GC and mass spec for non-methyl hydrocarbons, oxygenated VOCs, and the very high precision isotope measurements that I was talking about that we need. They really can only be done offline or by lab mass spec. So we did purchase an Aerodyne ICL system that can measure, in principle, carbon-13 isotopes, and we're still evaluating the use of that, but you can really only see really strong changes in carbon-13 with a real-time instrument. Really, we're relying on these whole air sample systems. And we also do some remote sensing. So we have a nadir pointing Fourier transform infrared spectrometer that we can do retrievals of methane, nitrous oxide and columns to the ground. And all of those is what we've used. And I just wanted to show you a few photographs from some of the field campaigns we've done around the world. So it's not just Africa that we've been lucky enough to go here with the various carbon projects we've been doing over the past 10 years. This is a photograph over Svalbard in 2013, where we were measuring emissions from the Arctic wetlands. So we were flying over Svalbard to look for evidence of hydrate emission or geological seeps offshore Svalbard. We didn't see any. That was probably a good result to get. But that's a photo over Svalbard. And this is a photo over the wetlands of Finland, again in July 2013. People are often shocked when I show this because people assume that the Arctic is always frozen. It's actually a beautiful place in the summer. And I think while we were there in 2013, it was actually warmer in northern Finland than it was in the UK on this day at 21 degrees. But it's that temperature that gives you the methane. So that swamp you can see in the photograph is emitting large quantities of methane into the atmosphere. Right, so on to what we did in Africa. So the first of the three campaigns that I'm going to talk about is the one in Senegal that we did in 2017, in March 2017. So the flight tracks of the aircraft you can see on the right-hand side there. So we did 3 flights over southern Senegal in the Casamance region of Senegal. And we did some flights offshore off the coast as well. So in Africa, you typically get this easterly flow blowing emissions off into the Atlantic. That's what gives us Saharan dust storms and fertilizes the Amazon rainforest, after all. But the other part of this project was to look at how the evolution of fire plumes happens as they move offshore. So there was also an aerosol chemistry component to this project as well. But the flights I'm going to show you mostly today are the flights over the land surface, where we were measuring emissions from fires in the area. And we were doing that to measure the isotopic source of the biomass burning in the region and look for emission factors that could be useful globally. This is the team on the top left, and a picture of one of the much smaller fires on the bottom left. And one of the recurring themes of working in Africa is bird strikes. So not for the first time in the MOYA campaign did I worry for my life on this project. So bird strikes are a particular problem in Africa. A lot of the birds in Africa are very large and they fly at very high altitudes. So while we were working in Senegal, a Thomas Cook flight had to make an emergency landing because of a strike in Gambia. We did have a bird strike while we were there on the nose of the aircraft, which dented the nose of the aircraft. Luckily, they were able to get a replacement nose for the aircraft very quickly, which allowed us to carry on with the campaign. And we'll come back to what happened in Uganda with bird strikes a little bit later on. So Senegal, the southern Senegal, the bit that's south of the Gambia, is this gradient between Saharan Africa and sub-Saharan Africa. So we're gradually going from shrubland into what the CGLS land cover classification calls unknown open forest type, helpfully, but it's changing from shrubs to forest. So the area that was burning on this campaign was a mix of cropland, herbaceous vegetation, and forest. And this is what was going on at the time. So this is a plot from MODIS on the day. So we can see where the fires were in the red box. And on the top right, for anyone that's interested in biomass burning, you can see where the burning happens in Africa. And it's really on the bounds of the intertropical convergence zone. So as the ITCZ moves up and down, when it's the dry season, burning happens, and when it's not, it doesn't. And there's a belt in the middle where it's permanently wet, and that's what you see. So the fires that we sampled here in the Casamance region looked a little bit like this one on the bottom left, and you can see the data on the top right. So, and the flight track on the top left. So we were flying backwards and forwards, looping around and going back and forth through these fire plumes at different altitudes, all the way from 1,200 feet all the way up to 6,000 feet. And you can get a picture of the scale of these fires when you look at the altitude range there. The plumes that we were measuring went all the way up to 6,000 feet. And the photograph in the bottom left doesn't do it justice, because one of the largest fires that we flew through at multiple levels, for most of the time in the cockpit, the picture that you could see outside of the aircraft was just an orange glow with no visibility. Some of these, and we saw fronds from trees, hitting the aircraft, and the aircraft actually had charcoal on stains on the wings when we landed after this. So these were some really powerful and active fires that we measured. So what does all of that risking your life give you in the end? Well, it gives you something pretty boring after all. It gives you a table and a paper. Pat wouldn't like me calling it as boring at all. But this is what you get in the end, which is very useful. So you get a picture of what the emission factors are for this burning biomass. So the measurements that are highlighted there in the red box from Senegal show that we typically measured a range between 1.4 and 2.4 grams per kilogram of burnt fuel of methane emitted. And that's useful because if we know how much of a certain fuel type is burning from MODIS, for example, and we know what the emission factor is for methane, in this case that we've measured regionally, then we can tell what the flux of methane should be from that biomass burning. So the conclusion from the Senegal route was really that it agrees well with an uncertainty for savanna and grassland, but with a low mean. And we need these regionally specific emission factors as well as the isotopic sources to help us with the global budgeting. And of course, the other thing that we were doing in Senegal was to measure the isotopic composition of the burning source as well. So this plot here shows a Keeling plot, which tells us what the depletion of carbon-13 is in the methane. So we measured there that a source of around -34 per mil, which is heavier than the bulk global signal, varying from 28 to 34 per mil for different sample plumes. And to give the game away a little bit, the isotopic composition from biomass burning that we've measured across Africa is variable. So it's heavier in some places and lighter in others. It was lighter in Senegal. So we can't take a single isotopic value for biomass burning. We have to know what the regional signal is to be able to co-constrain these budgets. Right, so on to what we did in Uganda next. So in 2019, in January 2019, we went to Uganda and we were based in Entebbe Airport. So the team there on the bottom right, and a picture out of the aircraft showing some of the fires that were happening, and the much greener vegetation is on the top left. And I sort of come back to birds. So on the bottom left is a photograph in the cockpit, and you can see something on the windscreen there, and you can guess what that is. I have another photograph of what the aircraft looked like after taking off from Uganda as we were finishing the project, where we counted at least 20 bird strikes, and it was actually potentially a significant emergency. I can remember sitting in the back of the aircraft, and the pilots over their comms were saying, birds, more birds, even more birds. And luckily none of them went through the engines, because if you've got lots of birds going through aircraft engines as you're taking off, this is pretty dangerous. So this was the second time that I feared for my life on the MOYA campaign. And in Uganda, we were there to, again, study biomass burning, but also urban emissions and emissions from the wetlands in the area. So this was the end of the wet season in January 2019. And the flight tracks is what you can see on the top right. So we were flying over Lake Kyoga, which is a wetland system in central Uganda, Lake Victoria, you can see on the bottom of the plot, and some other smaller lakes like Lake Wamala to the west there. And then focusing on the fires, which were more predominantly happening in towards the northwest. So those sort of complex flight tracks where you can see lots of swirls on are us moving backwards and forwards, sampling individual fires in the northwest of the region. And this is the type of thing that we measured. So for one of those flights measuring fires in the northwest, we were able to measure the isotopic composition of the burning sources, and they are very much heavier than the global bulk source, with a range from -28 to -16 per mil. So a very big change compared to what's happening in Senegal. So you can see this bimodal distribution in the plot from Sherwood et al. There on the slide, with two modes for biomass burning. So our -28 to 16 stretches across both of these. So really, we need to get a much better handle on what's happening with biomass burning in different geographies, because it does vary, and it varies even within Africa. And then the final result is comparing the emission factors for methane from the fuels for Uganda. So we get a range there from 2.8 to 5.2, which compares with the Andre Bible, really, of biomass burning emission factors of 6.5. So the Uganda fires were a mix of forest and savanna, but the range was in between the two. And that's probably because there are more C4 plants in Uganda than Senegal. So knowing the correct mix of fuel types locally is absolutely crucial for global budgeting of fires. And that remains a challenge for us, because remote sensing can't tell us that. So the only way we're going to do that is with field campaigns. And we need to know what those emission factors are for different geographies. From the isotope story, so the wetland emissions in Uganda were much lighter than the global bulk source. Again, that's consistent with the global trends that we've seen since 2007. But to close the global budgets, we also need to know what the fluxes are. So the final part of the presentation is talking about the third part of this campaign, which was in Zambia. And this was my favorite bit of MOYA. I feared for my life a little bit less on this campaign. There weren't quite so many birds, and it was a much better place to operate. And we were surveying wetlands, and we were attempting to calculate fluxes from the wetlands, not just measuring the isotopes and emission factors, but using flux-based approaches. So we're in February 2019, we moved from Uganda to Zambia. It was still wet, it was the end of the wet season, and we were based out of Kampala Airport. And there were very few fires in the region compared to the other parts of Africa that we went to. So there's three areas here that you can see highlighted so in Zambia. So the Lake Bangweulu in the northeast. And these are the flight tracks color-coded for the measured methane concentration. Lukanga Swamp, a freshwater swamp, in central Zambia. And we had a lovely northwesterly wind on this day coming in this direction. So you can see that the methane enhancements line up with the direction of the wind as we go over the swamp itself. We're going to look at the results from that shortly. And the Kafue Flats, which is a much more heterogeneous system. It's a river system with tributaries, so that the heterogeneity in the methane there is explained just by the variation in the wetlands. Whereas Bangweulu and Lukanga were much nicer features to survey because they're almost square, which lends themselves very nicely to trying to do fluxes. And we had another task while we were there. We were hunting for helium. I'm not going to talk too much about that, but the Kafue Flats were really was of real interest to Zambia and University of Oxford, because there was potentially helium seeps, and there's a global shortage of helium. We won't talk about that. Right, so here are those three flight tracks again. Typically, each flight was about 4 hours. And you can see on a common color scheme, the measured methane concentrations. So the one that sticks out is Bangweulu. We see these very big hotspots in methane over this region here that doesn't look wet. So the darker colors are the open lake, and this bit in the middle is vegetated marshland. And that's where we saw the biggest emissions. And then Lukanga Swamp, you almost lose that gradient in methane concentration here in the southwest because of the color scale. And the Kafue Flats. And before we just go on to the fluxes, just to talk about what the result of the carbon isotopes was from the MOYA campaign in Zambia and Bolivia. So this is South America. So this is an all-campaign plot, the Keeling plot of the isotopic composition of the methane from wetlands in South America and Zambia put together. And it gives us, so the two dashed lines you can see on there are the two different continents. But they line up almost perfectly to give us a very consistent source for tropical wetlands of -59.3 per mil. So a very highly consistent global tropical isotopic signature for C4 plants and wetlands there, which is very much lighter than the global source. But fluxes, how do we do it? So I know you guys use this method. To calculate fluxes from aircraft measurements, we simply use a volumetric mass balance. So we treat the atmosphere as take some closed volume in it. We measure the wind vector. We measure the mixing height that a plume of methane might go to. And we use this equation, which is just an integral over some plane that you can measure downwind of a source, where you take the vertical and the horizontal axis perpendicular to the wind, and you integrate the difference between the measured methane enhancement and some background that you've managed to evaluate. So it's a relatively simple equation, but in practice, getting fluxes out of this creates a lot of scientific challenges. And this is what it might look like in practice. So it is an idealized case. If we've got some sampling by an aircraft at different altitudes and we spatially interpolate it using something like kriging, we can build up a nice picture of what the plume looks like in 2 dimensions. But as anybody that does mass balancing will tell you, it very rarely looks like that. So let's move on and quickly look at the results from some Zambia using the mass balance approach. So this is a picture of Lake Bangweulu. In Afrikaans, it translates as where the water meets the sky. And using the mass balancing approach, we measured that this one wetland system in Zambia was emitting around the equivalent of 1 teragram of methane per year. That's equivalent to the UK's entire methane emissions inventory. So this stuff really does matter. And if we look at where that methane is coming from for these 2 examples, Lukanga and Bangweulu, in Bangweulu, it's coming from this green region, which is permanent marshland. And we don't see any emissions at all coming from the open water body. And this is the nub of the problem with the models that try to predict methane emission from wetlands. Because at the moment, they treat all wetlands as being equal and just use the wetland area as the proxy for giving you the methane emission. What we're finding time and time again around the world, and this is in the Arctic, South America, and Africa, is that open water systems, open water bodies, even if they're shallow, they're not emitting much methane at all. We don't see it. The methane is coming from the regions where it's vegetated, where these permanent marshland regions, where there's vegetation that's able to grow through the water. So very shallow bathymetry, but plants are able to grow through it, especially C4 plants. And they are the conduits that bring the methane from the water column and the soils to the atmosphere. And really this focus by the models on getting the wetland area extent right is probably the wrong direction. We need to be looking at the processes, the vegetation mediated processes of how that methane is getting into the atmosphere. I'm going to skip ahead a little bit because I'm running out of time. A couple of technical things. For anybody that's at Stony Brook that's doing mass balancing, you'll know this problem. One of the problems with mass balancing is that if your boundary layer is growing faster than your boundary layer can mix, it creates a real headache. And this is one that we had to put a lot of attention to into getting right in Africa, because tropical boundary layers grow extremely quickly in the morning. So we had to do a lot of work for getting the dilution effect right and the entrainment effect right of a growing boundary layer. So for the nerds who are doing mass balancing at Stony Brook, if you're interested in this, Joe can tell you about it, or we can tell you about it. And this is all going to be in a paper that we're going to submit, hopefully to Nature in the next few weeks. So final results. We did a lot of work trying to calculate the mass balance fluxes and then comparing them to satellite measurements and inversion models. So what you can see here on the left are the measured methane concentrations with time in red. An emissions prior, which you can tell is useless. That's coming from the carbon models of what they think the emissions might be contributing to the atmospheric measurement. And then we fitted the emissions in the inversion models to try and recreate the measurement. So we did that very successfully. And if you do that, the plot on the top right shows you that you can get very good agreement with what you can measure by satellite. So in this case, Tropomi and GOSAT. So when we compared our measured enhancements with the Tropomi and GOSAT enhancements, we got very good agreement. But even though the measurements and the satellites all agree. Nothing agrees with any of the models in the Global Carbon Project. So you don't need to look at every model that's listed on the x-axis there on the right-hand side, but those are all of the carbon process models that are used and land surface models that are used in the Global Carbon Project. So we extracted the area flux, the area average flux for the different swamps that we sampled in Zambia. So those are the blue and the pink colors. And then we compared them with what we actually measured, which are the green colors. And this isn't even just an order of magnitude in some cases. This is some models are predicting no emissions whatsoever, and we're measuring very significant emissions. There was one model called Visit, which was within error with our measurements. That's a model that has a different parameterization for vegetation, which I think tells you the whole story. That this is not about wetland area extent. It is about vegetation mediation of that methane and shallow wetlands that matter. So to conclude then, what do we know about global methane? We know that methane concentrations are rising fast. We know that the sources are biogenic and thermogenic, but we can't balance those budgets at present or recreate them in the past. So all sources are rising, but some are rising faster than others. And we think, or at least I think, that those sources that are rising fastest are the biogenic sources. And of course, all of that means that it makes prediction of the future climate very difficult. So what are the unknowns? Will we pass a methane tipping point, or indeed have we already? Are there positive feedbacks that could be tripped that cause more and more methane to be emitted that could dwarf our efforts to reduce fossil fuel methane? And what will that mean for climate change? What's the correct source and sink balance? Can we mitigate it? And the question that we need to, I think all of the papers we're all publishing are saying the inventories don't agree with what we measure. The process models don't agree with what we measure. But how do we improve this? That's, if I see another paper that just says that nothing agrees, we have to get, I think, the modelers to work on this problem and understand the measurements that we're taking, how you can use those measurements to reparameterize the models to get them right. I don't think comparing them ad infinitum is going to help us any further. So to conclude, the strong and growing evidence, in my opinion, that positive feedbacks in the tropics have probably already been triggered. And we see that in tropical Africa and South America. So some sources can be controlled, fossil fuels, so we need to do that now. This narrative that CCS is going to come to the rescue is not an excuse not to do that now. But we need to understand the biogenic processes better urgently, because the models aren't capturing them. And we need to target those measurements to where we have underrepresented sources, and most of those are in the tropics and in Africa. So more work is needed in Africa and probably the Arctic too, to understand the biogenic processes. And then to make sense of it, we need a global flux measurement system and co-constraints for global budget modeling, probably with isotopes, probably not so much with ethane, but isotopes and methane together are a really powerful mix for closing the budget. And satellites offer a lot of promise, but they can't do everything, and they can't measure the carbon isotopes. And the final point, there is no winner in the global methane debate. All sources are growing, some faster than others. And lots of the papers I get sent to review or see fall in on one side or the other and talk about either biogenics as dominating and therefore explaining the trend, or fossil fuels as explaining the trend. We need to move past that as a community, I think, in methane world, and not pick winners in publications, because all sources are rising, some are just rising faster than others. As the final thing to leave up is the name of all of the people that were involved in the project there, so you can look at that list while we're taking any questions. Thank you very much, Joe.
Great, thanks, Grant. That was really interesting. Does anyone else have any questions first before I launch in with some? Anyone want to put their hand up or just chip in? Oh yeah.
I'll stop the screen share now. There you go.
Okay, cool.
I'll help into it.
Yeah, go ahead, Kamazim.
This is Mary Scranton. Can I ask a question?
Yeah, sure.
What is the current thought about methane hydrates? Because that's, I mean, among the oceanographic methane community, people have been desperately trying to see destabilizing hydrates for 40 years. And my sense is that they keep measuring it and they keep not seeing any methane going into the atmosphere. And I just wondered, I've been away from the field a little bit for a while, and I wondered what the current thought of this was.
So it's a very minor source, if at all. So the range is 2 to 9 teragrams of methane to the atmosphere from hydrates, but measurements aren't really seeing it. So, but there's a nuance there. So we did some flights in the Arctic off Svalbard to see if we could measure it, and we saw no evidence of any enhancement of methane whatsoever. So what we did in a paper with Katrin Lundmeyer at NILU in 2015, I think it was to characterize what the minimum possible flux of methane to the atmosphere from the ocean associated with hydrates could be within the measurement error that we had from the instruments on the aircraft. And we concluded it was very low, and I'll have to send you the paper. But I think the consensus on hydrates is that they remain very stable at the moment. That they're still under enough pressure and they're still cold enough that they're not being liberated. But this isn't an area I work on so much. I think other people know more about it. But just to come back to the whole source from the ocean to the atmosphere in the Arctic, when we were there, the winds were very slight, the sea was very calm, and Shakova's work in the Arctic, which has looked at measurements of emissions from the ocean surface to the atmosphere, were in more disturbed, stormy conditions. And there's an interesting piece of science there that, you know, when the ocean surface is disturbed, methane is emitted to the atmosphere, but the ocean, the water column can actually be supersaturated in methane and not emit anything to the atmosphere in calm conditions. So there is a meteorological feedback, I think, on emissions.
Well, also bacterial. I mean, the bacteria, if it's calm enough for the bacteria to get it to first, it seems like a lot of it is going into carbon.
Yeah.
No.
Yeah.
Thank you.
So it's not making it out of the column. But yeah, I think the consensus is that the hydrates are relatively stable. But I can't say I'm an expert on it though.
Yeah, on just to chip in on that Shakova study, I think one of the things, like certainly in their original study, one of their assumptions was that the biogenic, that the microbial uptake of methane in the column was like significantly small, that it would just like, all you had to do was measure the methane coming into the ocean column, and it would just build up there until there was a storm, and then it would all be released. I think that I don't know much about like ocean stuff, but I think other people, I think that was one of the things that was criticized about the study, was that like that's quite an out there assumption, at least in general. Maybe it's the case in their like specific place they measured, but like in general that there is conversion to CO2.
Yeah, I think I may have seen some of those early proposals, and they didn't actually, well, I don't know what they ended up, they suggested that would be enormous fluxes, but they didn't actually see high methane in the air. So anyway, thank you very much for your comment. Yeah,
there's been news articles in the press here over the years calling it, you know, the Arctic time bomb and all this kind of thing. I think people think that they're probably quite stable for the near future. And not a source to really be worried about. I think probably the thing we need to be worried about is whether we end up trying to make use of them as a fuel. That would probably be the disaster. Let's hope that doesn't happen.
Right. Thank you.
Kamazina?
Thank you very much, Grant, for a nice talk. I'm going to start with a piece of advice. I think your next adventure should be to go to the SAD in Sudan.
Yes.
But my question was on your first bullet on the conclusion, where you say there's evidence to show feedback is already set in. Maybe I don't know this because it's not quite my field. I'm an oceanographer, by the way. There have been very few measurements on Africa on such a scale you've done. I think some Germans have done that before in West Africa and stuff. But so if there have been so few measurements, what evidence do we have that really these sources are increasing?
Well, you've hit the nail on the head in that we don't have measurements of these fluxes historically. So we don't really have the comparison to make really well. So what's clear is that the models are not capturing those emissions. So there is a source in the tropics that the models aren't capturing. And everything we see, and this includes in the Arctic, is that it's something to do with vegetation. Now, we know that the tropics are warming and becoming wetter. So yes, it is a bit of a leap of faith to say that feedbacks might have been triggered. But given the trend in the isotopes, which is very clearly towards lighter isotopes, so it's pointing towards increased biogenics growing fastest, that's clear. Methane's rising. And there's this source that the models have never been capturing in the tropics. Those things put together lead you to a conclusion that might say that there's an accelerating increase in methane emission from the tropical wetlands. But yeah, it's by far, it's not a foregone conclusion for sure, yes.
Okay. Thanks.
It is a leap of faith. I don't think we have the data set to measure a trend yet. I think satellites will start to do that. And you're right, the SUD. So Mark Lunt wrote an excellent paper in 2019 looking at troponin measurements over the SUD. And yeah, there's even more methane being emitted there than Zambia, Uganda for sure. Yeah.
Thank you.
Anyone else want to chip in with a question? If not, I'll ask one then, which is on another one of your conclusions, Graham, which is that all of the sources are increasing, but some are increasing more quickly than others. I'm just gonna, like, how do we know that? How do we know that it's not the sink? Yeah, how do we know that it's not OH changes in OH? You know, like there's been papers like Alex Turner's paper that says that the sources are actually decreasing, and there's been a few papers that say that at least the fossil fuel sources are decreasing, and that it's kind of compensated for by the fact that the sink is also decreasing faster. So do we know that is the case, or you know, is it a case about the OH being buffered? What do you think?
Well, so it's not just about global budgeting that tells you that all sources are increasing. So the other thing that tells you that all sources are increasing are the inventories and the measurements. So the IPCC storylines, you know, if you believe them, tell you that the national inventories are increasing. So global anthropogenic carbon is increasing. Biogenics are increasing because of the isotopic picture. So with those two pieces of information together, you can say that all sources are rising. And by all sources, I mean thermogenic and biogenic. I don't mean specifically geological seeps or landfills. I just mean that the two biogenic and thermogenic, they are definitely both increasing, and that's a convolving picture from the inventories and the carbon isotope story. But yeah, you're right. There's all this debate about OH and biomass burning as well, and for sure that might be part of the story. So I think that the message, perhaps, that I should have amended my final point on the conclusion slide and said that we all need to keep an open mind about it all, because yes, there's probably a change in the OH sink and we need to account for that. But I stand by the point that all sources are increasing, but some are rising faster than others.
Anyone else? Okay, I have a more specific question about that visit model that agreed, the one model that agreed with the measurements. Does that model, do you know if that model has much larger global emissions, or does it just have the emissions in the right place? You know, compared to the other models, does it have a much larger total?
It's a good question. I don't know, and Jacob's still looking at that. So Jacob Shaw is the best person to ask. To be honest, we've had a bit of difficulty understanding the models. I think we need a better interface with the modelers. So we're still looking into why that model is the best agreement. But we know it has a different vegetation parameterization, and we've looked at the maps of the emissions, and it has much higher emissions over the areas of marshland that I showed in Zambia, whereas a lot of those other models show zero flux from the marshlands. So yeah, but we need to look deeper into what might be right about the visit model.
Cool, yeah, that makes sense. And anyone else? Okay, well, if not, then I guess just do a virtual clap. Thank you very much, Grant, for
no worries. Yeah,
thanks very much for the talk. And yeah, sorry that you couldn't come and do this in person as we planned last year, but
one day.
It's great. Yeah, one day. Yeah, it's great that we managed to hear from you, albeit a year later than originally planned.
No worries. All right, thank you very much, everybody.
Nice one.
Cheers,
right.
Joe.
Cool.
Cheers.
Thanks.
Bye.
Okay, bye.